Good morning, boys and girls, and welcome to our next lesson having to deal with limits. Today we're going to talk about continuity and again kind of review some of our one-sided limits. So real fast here is our definition for continuity, if a function is continuous or not. Okay? These same three rules everybody uses. You must have fulfilled all three rules, and we usually talk about them in this order. That way if there is an issue, we can say no because of one or no because of two, and we know what rule we're talking about. All right. So a function f of x is continuous at x equals c at some value c if the following things are true. 1. F of c must exist. The function must exist at that point. 2. The limit as x approaches c of f of x must exist. As I approach from the left and the right, I better approach that same value. And then now the third piece of that is when I'm approaching from the left and the right, that same value, the value that f is must equal that same thing, and if they're all at the same place, then the function is continuous. So this is our formal definition of continuity, and this is the one that we're going to use as we move forward. You're probably going to want to write that one down. Okay, now that we know how to tell if a function is continuous or not, next we're going to look at the different types of discontinuity we have when a function is not continuous. All right, so we're going to look at function f of x here, and if I were going to try to graph this function, we're going to look at its discontinuity. First thing you might do is try to factor the top. This is like x minus 2, x minus 1, all over x minus 2. We're going to kill off the x minus 2's. And so that's creating a hole, which again, if we know graphically, that's going to create a place of discontinuity. And we're left with x minus 1. So this function, if I were to graph it, would look like the graph of x minus 1. Kind of like that. Just though at x equals 2, because I killed that off, we are going to have, oh geez, that's going to erase the whole thing, isn't it? I'll just put it in like that. We're going to have a little hole at x equals 2. Okay? So that's what this function looks like. This piece of discontinuity here is known as a removable piece of discontinuity. Okay? Because if I wanted to, I could make this a piecewise function, and I could actually go and, then fill in the hole. And then the function would be continuous because it exists from the left and the right approach the same side, and all those things are equal. Okay? Before, when there's a hole in there, that would fail rule 1 of our continuity rules. So this is a removable discontinuity. Removable discontinuity. All right. Now the next type of discontinuity. Okay, now we're looking at the same function, just the reciprocal of it, so I just flipped it around. So a lot of the same things are happening. I'm going to factor this thing, x minus 2 over x minus 2 times x minus 1. Now when I kill stuff off, we are left with 1 over x minus 1. But now when I try to go graph this function, because that x minus 1 is on the bottom, this is going to be a vertical asymptote at 1. And it would look something kind of like that. All right. So this is what we refer to as a non-removable or jump discontinuity. Okay? I can't go and get rid, like before I could fill in the hole, and that removes my discontinuity. This one I can't get rid of the asymptote. There's no way for me to do that. And we call it a jump discontinuity because as I'm drawing with my pen, let me change color so you can see me drawing. But as I'm drawing with my pen, I have to literally, I've got to jump and lift my pen up to go to the other piece of the graph. So that is a non-removable or jump discontinuity. The two different kinds we deal with. So make sure you know the difference between the two. All right. Next, we've already talked about one-sided limits, so I'm not going to bore you too much with those. I think we have a pretty good hand on one-sided limits because we've discussed that to some extent. We're going to move on to if we have a composite function, limits of composite functions. Okay. So we first have some rules. If g is continuous at a, and f is continuous at g of a, okay? Those two things have to be true. But if those two things are true, then the limit as x approaches a of f of g of x equals f of the limit as x approaches a of g of x. Okay, so here's one more little rule we can use when we are dealing with a composite function like this. Just so long as g is continuous at a and f is continuous at g of a. Okay, we can use this thing. It's kind of handy. This doesn't pop up a lot, but it will pop up occasionally. It's a good thing to know. Okay, so for our first example here now, we want to look at this function and we want to discuss where it is not continuous and why, which rule it violates. So normally in class I have you guys just pick a point and start talking about it, but I guess since nobody's here, I will do it myself. If I'm talking about like at x equals 1, it is discontinuous. And I got to run through my checklist. Does it exist at 1? Yes, it does. It exists at 1 right there, right? Does the limit exist at 1? Rule number 2. Well, yes, the limit exists at 1 because as I go from the left and as I go from the right, they're both approaching 2. So the part where this breaks down, why this is not continuous at x equals 1, is because part 3, the limit from the left and right does not equal the value of the function. Okay, so that violates rule 3 or part 3. All right, at x equals 2. Okay, here, again, going through my checklist, does it exist at 2? Yes, it does. Right there, right? Does the limit exist? Well, from the left and from the right, we're going to 2 different areas, so no. This violates, part 2 or rule 2 of the continuity checklist. Okay. Next one, at x equals 3. At x equals 3, this is discontinuous. And again, just start down your checklist. Does it exist at 3? No. There's an open circle there, no. So this fails part 1 of the continuity checklist. Okay. So again, be familiar with the 3 parts of continuity. You can refer to them as part 1, part 2, part 3, rule 1, rule 2, rule 3. Okay, we all know when you say it violates rule 1, that means the function does not exist at that point. It violates 2, the limit does not exist then. Okay, so be familiar with the 3 rules and the order they go in. Okay, number 2 here. We're given a function f of x as a piecewise function, and we want to find out, is it continuous at x equals -1? So this one we're going to kind of approach more algebraically. But I'm going to follow the same checklist. Does it exist at x equals -1? Well, the answer to that is yes, it does. At -1, the function is 2. So that passes the first part. Now the second part. Does the limit exist as x approaches -1? So I'm going to look at this. I would start by factoring out the x plus 1, since when I plug it in, I'm going to get 0 over 0. And so those cancel off. And so this limit would be -1. Now the third piece then, do those 2 things equal each other? In this case, no, they do not. F of -1 does not equal the limit as x approaches -1 of f of x. Therefore, this violates rule 3. Okay? So the function exists, the limit exists, but they did not equal each other. Okay, on this next one, it's asking us to find determine the intervals on which the following functions are continuous. Okay, so if we have a rational function, hopefully from our algebra knowledge, we can agree that this is going to be continuous everywhere except there is a hole or an asymptote. Right? Those would be my places of discontinuity. So to find those things, I'd want to try to factor and kill things off. In this case, I cannot factor the top, but I can factor the bottom. So that means there are no holes, but I do have some asymptotes going on. Again, we have a vertical asymptote when the bottom equals 0. So in this case, we have an asymptote at 3 and -3 and at 3. Okay? So that means my function is going to be continuous on the interval from -infinity to -3, and then -3 to 3, and then 3 to infinity. Okay, those are my intervals of continuity. Okay, boys and girls, here we go. Our very last one. We're given the function e to the square root of x. We want to identify when this function is continuous on the intervals in which it's continuous. And then we need to talk about the limit as x approaches 4 of f of x and the limit as x approaches 0 of f of x. I guess first and foremost on this one, we're going to want to, this is going to be continuous, I guess. Thinking about this, these are continuous anytime the function is defined. So this function is defined from 0 to infinity. So that'd be it's going to be continuous on 0 to infinity. If I go to evaluate the limit as x approaches 4 of f of x, again, very first step, you should do every time, plug in. So if I do, e to the square root of 4, well, I guess this would be e squared. And then now the very last one, same thing, limit as x approaches 0 from the right. Very first thing you should do is plug in. So I get e to the square root of 0. Square root of 0 is 0. E to the 0 is 1. So just playing around with our different one-sided limits in general, and continuity. Hopefully this lesson treats you all well. We have some worksheets along with this stuff. Good luck, and come to me if you got questions. Bye.